Imagine looking at a photograph of your great-great-great-grandparents. Now, multiply that great by a few billion. That's essentially what the James Webb Space Telescope does when it observes galaxies 13 billion light-years away. But how does it actually work? How can a telescope, even one as advanced as James Webb, see objects so incredibly distant that their light has been traveling toward us for most of the universe's history? Today, we're going deep into the science and engineering that makes this possible. We'll explore the clever physics, the cutting-edge technology, and the ingenious methods that allow James Webb to observe the most distant galaxies in the universe. This isn't magic, it's something better. It's physics and engineering working in perfect harmony. The fundamental challenge. Let's start with the most basic question. Why is observing distant galaxies so difficult? There are actually several compounding problems. First, there's the obvious issue of distance. Light from these galaxies has traveled for over 13 billion years to reach us. During that journey, the light spreads out in all directions. By the time it reaches Earth, only a tiny fraction of the photons emitted by that distant galaxy enter our telescopes. Think of it like this. Imagine a single candle 13 billion light-years away. The light from that candle spreads out over an expanding sphere. By the time it reaches us, those photons are spread across a sphere with a radius of 13 billion light-years. The amount of light hitting any particular spot, like a telescope mirror, is infinitesimally small. But distance isn't the only problem. There's also the expansion of the universe itself. As the universe expands, space itself stretches. And when space stretches, it stretches the light traveling through it. This phenomenon is called cosmological redshift. Light that was emitted as high-energy ultraviolet or visible light gets stretched into lower-energy infrared light as it travels through expanding space. Galaxies 13 billion light-years away emitted most of their light in the ultraviolet and visible range. That's what stars produce. But by the time that light reaches us, it's been stretched all the way into the infrared, particularly the mid-infrared range. This is crucial because our atmosphere is largely opaque to mid-infrared light. Ground-based telescopes simply can't observe at these wavelengths. You need to get above the atmosphere, into space. And even then, you face another problem: heat. Everything warm emits infrared radiation. Your body glows brightly in the infrared. So does Earth. So does the sun. Even the telescope itself, if it's warm, glows in infrared and creates overwhelming background noise that drowns out the faint signals from distant galaxies. So, to observe the most distant galaxies, you need a telescope that is, in space, optimized for infrared observations, extremely sensitive to faint light, and kept incredibly cold to minimize its own infrared glow. That's James Webb. The infrared advantage. Let's talk about why infrared vision is James Webb's superpower. When we look at the nearby universe with optical telescopes, we see galaxies in visible light, the light our eyes can detect. But visible light tells only part of the story. A lot of activity in galaxies happens behind veils of dust. Dust absorbs ultraviolet and visible light, but is transparent to infrared. When you observe in infrared, you can peer through dust clouds and see star formation happening inside molecular clouds, stars forming in dusty galactic cores, and the structure of galaxies that would be invisible in optical light. But for distant galaxies, infrared isn't just useful, it's essential. Because of redshift, the visible light emitted by distant galaxies has been stretched into infrared by the time it reaches us. Here's a concrete example. A galaxy 13 billion light-years away has a redshift of roughly 10 to 13, depending on the exact distance. This means wavelengths of light have been stretched by a factor of 10 to 13. A photon that started as ultraviolet light at 100 nanometers wavelength arrives as infrared light at 1000 to 1300 nanometers. The Hubble Space Telescope can observe in near-infrared up to about 1700 nanometers. But for the most distant galaxies, much of their light is redshifted beyond even that range, into the mid-infrared where Hubble cannot see. Webb observes from 600 nanometers all the way out to 28,000 nanometers, 28 microns. This extended wavelength range allows it to see galaxies that are completely invisible to Hubble, or that appear as mere smudges in Hubble images but reveal intricate detail in Webb observations. The infrared capability also allows Webb to observe different features in galaxy spectra. Spectral lines, specific wavelengths where atoms and molecules emit or absorb light, are diagnostic fingerprints. They tell us what elements are present, how hot the gas is, how fast it's moving, and if there's an active black hole. In distant galaxies, these lines have been redshifted from ultraviolet and visible wavelengths into the infrared. Webb can detect these lines and use them to determine precise distances, measure chemical compositions, and identify physical processes occurring in these ancient galaxies. The mirror, collecting precious photons. Now let's talk hardware, starting with the most visible component, the mirror. Webb's primary mirror is 6.5 meters in diameter, about 21 feet across. That makes it the largest mirror ever launched into space, with a collecting area about 6 times larger than Hubble's. Why does matter matter? Because collecting area determines how much light the telescope gathers. Light from distant galaxies is unimaginably faint. Every photon counts. A larger mirror intercepts more photons, allowing the telescope to see fainter objects or to observe objects in shorter exposure times. But here's a key detail. You can't launch a 6.5 meter solid mirror into space. It wouldn't fit in any rocket. So, Webb's mirror is segmented, 18 hexagonal segments that fold up for launch and unfold once in space. Each segment is made of beryllium, a metal chosen for several important properties. Beryllium is strong yet lightweight. It holds its shape across a wide range of temperature, and it can be polished to an extremely smooth optical surface. But beryllium by itself isn't reflective enough in the infrared, so each mirror segment is coated with a microscopically thin layer of gold, about 100 nanometers thick, roughly 1,000 times thinner than a human hair. Gold is highly reflective in the infrared, making it the perfect coating for Webb's purposes. After deployment, each mirror segment can be individually adjusted. Tiny actuators on the back of each segment can move it with nanometer precision, tilting and translating it to bring all 18 segments into perfect alignment. This alignment process, called wavefront sensing and control, effectively turns 18 separate mirrors into one large, perfectly shaped optical surface. The result is a mirror that can focus light to an extremely sharp point, concentrating the precious photons from distant galaxies onto the telescope's scientific instruments. Staying cold. The sun shield. But having a large infrared optimized mirror isn't enough. Remember, everything warm glows in the infrared. If the telescope itself is warm, its own infrared emission would overwhelm the faint signals from distant galaxies. This is where the sun shield comes in. The sun shield is one of the most impressive engineering achievements of the entire mission. It's a 5-layer structure, each layer about as thin as a human hair, made of a material called kapton, coated with reflective aluminum and silicon. When fully deployed, the sun shield is about the size of a tennis court, roughly 21 meters by 14 meters. Its job is to block sunlight and heat from the sun, earth, and moon, creating a permanently shadowed region where the telescope and instruments can stay cold. How cold? The sun-facing side of the shield can reach 85 degrees Celsius, 185 degrees Fahrenheit, but the telescope side, shielded from direct sunlight, cools down to about minus 233 degrees Celsius, minus 388 degrees Fahrenheit. This isn't just cold, it's necessary. At these temperatures, the telescope's own infrared emission becomes negligible compared to the signals it's trying to detect. The 5 layers aren't just arbitrary. Each successive layer provides additional insulation. Heat radiates from one layer to the next, but with careful spacing and design, very little heat makes it all the way through to the telescope side. It's a bit like a high-tech thermos bottle, but instead of keeping coffee hot, it's keeping a telescope cold. The sun shield also has to remain in a specific orientation. Webb orbits at what's called the second Lagrange point, or L2, about 1.5 million kilometers from Earth.
At this location, the Sun, Earth, and Moon are always in the same direction, allowing the sun shield to block all three simultaneously. This permanent orientation is crucial. If the telescope had to turn toward the sun even briefly, the sun shield's effectiveness would be compromised and the sensitive instruments would heat up. The instruments, turning light into data. The mirror collects light, but the instruments are what turn that light into scientific data. Webb has 4 main scientific instruments, and each one is a marvel of engineering. Let's start with NIRCam, the telescope's primary imager, working at wavelengths from 0.6 to 5 microns. NIRCam is what produced those stunning first images, the deep field, the cosmic cliffs of the Carina Nebula, Stephan's quintet. NIRCam doesn't work like a digital camera on your phone. Instead of a single sensor, it has 10 different detector arrays, each optimized for specific wavelength ranges. The detectors
themselves are made of mercury-cadmium telluride, a semiconductor material that's sensitive to infrared light. When an infrared photon hits a detector pixel, it excites an electron, creating a tiny electrical signal. These signals are amplified, converted to digital data, and transmitted to Earth. By counting how many photons hit each pixel during an exposure, NIRCam builds up an image. But NIRCam does more than take pretty pictures. It also has coronagraph mode, which blocks the light from bright stars to reveal faint objects nearby, like exoplanets or circumstellar disks. And it can take images through multiple filters, isolating specific wavelengths to study particular physical processes. Next is NIRSpec, the near-infrared spectrograph. While cameras produce images, spectrographs split light into its component wavelengths, producing a spectrum. Spectra are incredibly information-rich. They reveal chemical compositions, temperatures, velocities, and physical conditions. NIRSpec has a revolutionary capability. It can observe up to 100 objects simultaneously. Using a micro-shutter array, a grid of thousands of tiny shutters that can be individually opened or closed, astronomers can select specific galaxies in a field and obtain spectra of all of them at once. For studying distant galaxies, this is transformative. Instead of observing one galaxy at a time, you can survey an entire field efficiently. This allows astronomers to build large samples of distant galaxies, studying their statistical properties rather than just a few individual examples. Then there's MIRI, the mid-infrared instrument. MIRI observes at longer wavelengths, from 5 to 28 microns. This is crucial for the most distant galaxies, whose light has been redshifted beyond NIRCam's range. MIRI is also special because it requires additional cooling. Even with the sun shield, MIRI's detectors would be too warm for optimal sensitivity. So MIRI includes a cryocooler, essentially a refrigerator in space, that brings its detectors down to just 7 degrees above absolute zero, or minus 266 degrees Celsius. This extreme cooling allows MIRI to detect incredibly faint mid-infrared signals. It can see through even the thickest dust clouds, observe forming planetary systems, study the atmospheres of exoplanets, and detect the most distant galaxies redshifted into the mid-infrared. Finally, there's FGS/NIRISS, the Fine Guidance Sensor and Near-Infrared Imager and Slitless Spectrograph. The fine guidance sensor is what keeps the telescope pointed accurately. When you're trying to observe objects billions of light years away, even the tiniest pointing error can blur your image. FGS tracks guide stars and feeds information to the telescope's control system, keeping it locked on target with milliarc-second precision. NIRISS is a scientific instrument in its own right, specializing in studying exoplanet atmospheres and searching for the first galaxies through a technique called GRISM spectroscopy, which produces spectra of all objects in the field simultaneously. Integration time. Patience as a tool. Here's something that might surprise you. When James Webb observes a distant galaxy, it doesn't just point and click. It stares for hours. Sometimes for days. Why? Because those distant galaxies are faint, really, really faint.
The brightness of astronomical objects is measured in magnitudes. Each magnitude represents a factor of 2.512 in brightness. A first magnitude star is about 2.5 times brighter than a second magnitude star, which is 2.5 times brighter than a third magnitude star, and so on. The faintest stars visible to the naked eye under perfect dark sky conditions are about 6th magnitude. Galaxies 13 billion light-years away can be magnitude 31 or fainter. That's about 10 million times fainter than your eyes can see. To detect something this faint, you need to collect photons over a long period. Think of it like filling a bucket with water from a tiny drip. If you only wait a few seconds, you might collect a few drops. But if you wait for hours, you accumulate enough water to measure. Similarly, if James Webb only observed for a few seconds, it might detect only a handful of photons from a distant galaxy, not enough to form a clear image or useful spectrum. But by integrating for many hours, accumulating photons over time, the signal builds up above the background noise. This is why deep field images are so valuable. When James Webb stares at a single patch of sky for dozens or hundreds of hours, it reaches depths that shorter exposures simply cannot achieve. Each additional hour of integration allows fainter objects to emerge from the noise.
There are clever tricks to maximize efficiency, too. Rather than continuously staring at one point, James Webb sometimes uses a technique called dithering. The telescope makes small pointing adjustments between exposures, shifting the image slightly on the detector. When the images are combined later, this improves the spatial resolution and helps remove instrumental artifacts. Another technique is spectroscopic multiplexing, which we mentioned with NearSpec. By observing many objects simultaneously, you get the equivalent of hours of integration time on each object, without spending proportionally more telescope time. Redshift, measuring cosmic distances. Once James Webb has collected light from a distant galaxy, how do astronomers determine how far away it is? The key is redshift, but measuring redshift requires understanding spectral features. Every element has a unique spectral fingerprint. Hydrogen, for example, produces a characteristic pattern of emission lines called the Lyman series. The strongest of these is Lyman alpha, which occurs at a wavelength of 121.6 nanometers in the ultraviolet. When astronomers observe the spectrum of a distant galaxy and see this Lyman alpha line, they can measure its observed wavelength. If the line appears at 1,216 nanometers instead of 121.6 nanometers, that's a redshift factor of 10. This means wavelengths have been stretched by a factor of 10 due to cosmic expansion. From the redshift, cosmologists can calculate distance and look-back time. A redshift of 10 corresponds to a distance of roughly 13.2 billion light-years and a look-back time of 13.2 billion years, meaning we're seeing the galaxy as it appeared just 500 million years after the Big Bang. But there's a challenge: photometric redshift versus spectroscopic redshift. When James Webb takes an image through multiple filters, astronomers can estimate redshift by comparing the galaxy's brightness in different wavelength bands. This is called photometric redshift. It's useful for quickly surveying many galaxies, but it's not perfectly accurate. Uncertainties can be significant, especially if the galaxy has unusual properties. For precise measurements, you need spectroscopy. By spreading the light into a spectrum and identifying specific spectral lines, like Lyman alpha or oxygen emission lines, or the characteristic break at 912 nanometers where hydrogen absorbs light, you can determine redshift with high precision. This is where NearSpec and NIRISS shine. They can obtain spectra of distant galaxies, confirming their redshifts and providing detailed information about their chemical compositions, star formation rates, and physical conditions. Gravitational lensing, nature's magnifying glass. Sometimes James Webb gets help from nature itself through a phenomenon called gravitational lensing. Einstein's general relativity tells us that massive objects warp spacetime. When light passes near a massive object like a galaxy cluster, its path bends. If the alignment is just right, the cluster can act like a cosmic lens, magnifying and brightening objects behind it. This lensing can amplify distant galaxies by factors of 10, 100, or even more.
Galaxies that would be too faint for James Webb to detect become visible. And because the lensing magnifies not just brightness but also apparent size, it allows astronomers to study the internal structure of these galaxies in much greater detail. James Webb has specifically targeted gravitational lensing clusters for this reason. Clusters like SMACS 0723, which produced the first deep field image, or El Gordo or MAX 0647, contain hundreds of galaxies. But more importantly, they lens and magnify thousands of background galaxies. One spectacular example is the Sunrise Arc, a galaxy lensed by a foreground cluster. The lensing stretches the galaxy into a long arc and magnifies it roughly 10 to 30 times. This magnification allows James Webb to resolve features within the galaxy that would otherwise be impossible to see. Individual star-forming regions, dust lanes, even hints of structure. Lensing also allows spectroscopic studies of otherwise impossibly faint galaxies. The magnification brings the galaxy's light above the threshold where NIRSpec can obtain a detailed spectrum, revealing its chemical composition and physical conditions. Astronomers use sophisticated computer models to reconstruct the lensed galaxy's true appearance. By understanding the mass distribution of the lensing cluster and how it warps light, they can reverse the lensing effect and see what the background galaxy really looks like. Gravitational lensing is a powerful tool, but it has limitations. You need a massive cluster in the right location and serendipitously aligned background galaxies. But when the geometry works out, it provides a unique window into the distant universe. Data processing, from raw photons to scientific images. When James Webb observes a distant galaxy, the raw data coming from the telescope isn't immediately usable. It requires extensive processing to turn detector readouts into scientifically meaningful images and spectra. First, there are instrumental effects that need to be corrected. Detectors don't respond perfectly uniformly. Some pixels are slightly more or less sensitive than others. Cosmic rays strike the detectors, creating bright spots that aren't real astronomical signals. Background light from scattered sunlight, zodiacal light, and the telescope's own thermal emission needs to be subtracted. These corrections are applied using calibration data and sophisticated algorithms. Astronomers take reference images, blank sky observations, internal calibration lamp exposures, and observations of well-characterized standard stars, and use these to characterize and remove instrumental artifacts. Next comes image combination. Because James Webb dithers its pointing, multiple exposures of the same field need to be aligned and combined. This process improves image quality and helps identify and remove transient artifacts like cosmic ray hits. For spectroscopic data, the processing is even more complex. The raw data from NIRSpec or MIRI is a two-dimensional image showing where light falls on the detector. But spectra are one-dimensional, flux as a function of wavelength. Extracting spectra requires identifying which detector pixels correspond to which wavelengths and which objects in the field. Wavelength calibration is crucial. Astronomers need to know the precise wavelength corresponding to each pixel to accurately identify spectral lines. This calibration uses internal lamps with known emission lines and observations of astronomical sources with well-characterized spectra. Once processed, the data is scientifically useful. Images reveal the positions, shapes, and colors of galaxies. Spectra provide redshifts, chemical compositions, star formation rates, and evidence for active black holes. But interpretation requires careful analysis. Not every faint red spot in an image is a distant galaxy. It could be a nearby cool star, or a background galaxy that's red for other reasons. Confirmation requires spectroscopy and detailed modeling. Pushing the limits. What's next? James Webb is already observing galaxies at the edge of the observable universe, but astronomers are continually refining techniques to push even further. One approach is to use the entire universe as a telescope through strong gravitational lensing. By carefully studying highly magnified galaxies, astronomers can test their understanding of galaxy formation under extreme conditions. Another is to combine James Webb observations with data from other telescopes. Ground-based observatories provide complementary wavelength coverage. Radio telescopes like ALMA can observe the cold molecular gas that fuels star formation. X-ray telescopes detect active black holes. By combining data across the electromagnetic spectrum, astronomers build the most complete picture possible of how distant galaxies work. And, perhaps most excitingly, James Webb will likely find things we don't expect. The distantest galaxy, the oldest stars, unusual types of objects that don't fit current theories. The history of astronomy teaches us that when we build more powerful instruments, we discover phenomena we didn't anticipate. Closing. So, how does James Webb observe galaxies 13 billion years away? It uses a massive mirror optimized for infrared light to collect every precious photon. It stays incredibly cold behind a tennis court-sized sunshield, minimizing its own infrared glow. It employs cutting-edge detectors and instruments that turn faint infrared light into detailed images and spectra. It stares patiently for hours or days, accumulating signals above the noise. It uses spectroscopy to measure redshifts and confirm distances. It leverages gravitational lensing when nature provides a boost, and it processes data with sophisticated algorithms to extract scientific information. Every element of the design, from the gold-coated mirror to the cryocooler on Miri, serves the single purpose of detecting the faintest, most distant light in the universe. This is engineering at its finest, complex systems working together to achieve something extraordinary. It's physics applied with precision to answer fundamental questions about our cosmic origins. James Webb doesn't just take pictures, it's a time machine, showing us the universe as it was over 13 billion years ago. And the science and engineering that make this possible are as awe-inspiring as the images themselves. Thanks for joining me on this technical deep dive. If you found this exploration valuable, subscribe for more in-depth looks at how space science actually works. Drop a comment about what aspect of James Webb's technology impresses you most. Keep looking up and keep questioning how we know what we know.